recently got a deal on some plasma globes on eBay, and while they are pretty neat, I feel like with the right modifications, they could be a lot cooler. Now I have a general rule that before I go tearing into stuff, I like to at least try the original product. Now what can you do with a plasma globe? Well, for one, if you put your hand on it like this, you get a little arc that goes up to your hand, which is pretty cool, but I mean honestly, this isn't going to keep me entertained for that long. Like, the thing isn't even a fire hazard. Is that too much to ask for consumer electronics? Now luckily this whole fire hazard issue can be simply solved with just a roll of aluminum foil. But first, a warning. The craziness that's probably about to unfold over the next 10 minutes or so was done completely for educational purposes. In fact, if you were to try any of this stuff at home, you'd probably die, so yeah, please don't do this at home. A piece of aluminum foil on top capacitively couples to that inner electrode, and now you can see it can draw more current. Now, you can even pull a little arc from the surface, which is pretty nifty. Now, I wonder what it feels like on my finger. Ooh, it actually tickles. Oh wow, it's cool drawing an arc from my finger. Alright, now it's time for a more important test, and that's whether it can burn stuff. So here I have a match, and doesn't seem to be doing anything. So I cover the match in aluminum foil, that way the foil touches me and can complete the circuit through ground. So, let's see if it lights the match. Now it's arcing. Not quite lighting yet.
One eternity later.
Yes, there it goes. Sweet. That was actually pretty cool. Alright, now I'm bored. This thing needs a lot more power. So I'm going to tear it apart. So I went ahead and tore down that plasma globe, and what can I say? I'm not impressed with this driver. I feel like Nikola Tesla, who actually invented the plasma globe, would be rolling in his grave if he saw this driver. Like, he was doing this stuff over 100 years ago, and this stuff was way better than this puny little thing. If you go on Google and look up how to make a high voltage circuit, this is literally going to be one of the first results. It's like child's play in the realm of high voltage electronics. But regardless, this thing works by using this 555 timer here to generate a square wave signal to this power transistor. And then this feeds into this flyback transformer where the rapidly changing current causes a relatively high voltage to be produced. And then it's fed through this long lead here into the plasma globe. So how do we make this thing stronger? Well, the dumb way would be to just feed higher voltage into the thing, but that's probably just going to blow the timer before anything interesting happens. So I guess the next best option is to feed a higher voltage into just that transistor itself. Or even better, use this transistor as an amplifier to feed an even bigger transistor, and then dump even higher voltage into that. Alrighty, so this is what the new setup looks like. So I start by feeding the output of this Scariac here into this IQ level 500 AC to DC converter. And from that feeds into this MOSFET here, which is the main switching component of the new driver. And it's funny because this power transistor here that was originally feeding the flyback transformer is now acting as just a little amplifier that powers the gate of this MOSFET. So yeah, let's give this thing a try. Man, I feel like this scene does such a great job of giving off the essence of hobby electronics. So let's dive right into this, because what could possibly go wrong? So let's start feeding a little bit of voltage there, and oh, it's way over. What's going on there? So apparently, due to my sloppy wiring, I ended up frying this little power transistor. But it's not like it really mattered in the first place, so now I just have the output of the 555 directly driving the gate of that MOSFET. So let's give this another go. Oh, sweet. Oh, something broke. Did it really fry that easily? No. It's trying to go. Oh, well look at that. I love when that happens. Let out the magic smoke. This project has been a great reminder of how much I suck at electronics. So I'm going to say screw this driver, and instead use a ZVS driver, which is much better. And also use a flyback transformer that's at least 10 times bigger. Not even the slightest glow? So that's how it's going to be, is it? You know, I guess it wasn't really the plasma globe's fault. It's probably the built-in rectifier inside that flyback transformer that's preventing me from getting nice arcs in the globe. Alright, screw this. I'm breaking out my massively overdriven car ignition coils, because if this doesn't do it, I don't know what will. Alright, let's give this thing a try. Well, it's certainly better. The noise is definitely an added bonus. But I still can't say I'm that impressed, like, there aren't even arcs shooting out of the glass. I think I can still do a lot better. Now, I'm sure if I were to drive those coils even harder, I could make the globe a little bit brighter, but really at that point I'm just grasping for straws, because what I really want is to draw the max amount of power I can possibly get from my electrical socket. I want giant arcs of electricity to shoot directly out of the glass. I want 1,000,000 volts to come from my driver to feed into the globe. Now, how does somebody like me generate 1,000,000 volts? Well, in fact, I don't need any fancy IGBTs or field effect transistors. In fact, I don't need silicon at all. What I do need are microwave ovens. Microwaves are full of parts that are useful for the electronics hobbyists and can be sourced for cheap or even sometimes free. So let's tear this thing down. Now I should point out that nobody without extensive electronics experience should ever go poking around in a microwave oven. Reason being, you touch the output of this while it's live, you're dead. You touch this without discharging it first, you're dead. You break this and inhale the dust, and before long borreliosis comes creeping in, slowly suffocating you and sucking every bit of life out of you until finally you're dead. Anyway, the main thing that I'm looking for is this transformer here. Now, unfortunately, it only does a little over 2,000 volts, but luckily I can string a few of them together for higher voltages. But I'm going to need more microwaves. I need transformers with relatively similar electrical characteristics. That way they don't fight each other when chained together. Now I found 4 that match each other quite nicely, and I wired the secondaries in series and the primaries in parallel, and of course accounting for phasing. Now if you try to chain any more than 4 of these together, then the voltage is just going to blow through the windings on the secondary. But even at just 4, this can be an issue. So to prevent this, I mounted them in these ammo cans here, and then I submerged them in mineral oil. Now this arrangement gives a voltage of about 10,000 volts. Which is certainly impressive, but still off by a factor of 100 of what we actually want. So now what? Well, this is where we get to look back at the ideas of Nikola Tesla. Not that one. And definitely not that one. He didn't even work on that. Can we just stop it with this whole free energy conspiracy already? Yes, that one. The magnifying transmitter. Or even better, the modern day equivalent, which is the aptly named Tesla coil. The Tesla coil is a type of step-up transformer, in which the primary and secondary sides form tank circuits, and they're tuned so that they resonate at the same frequency. They're capable of generating extreme voltages, well in excess of 1,000,000 volts. Now luckily, many of the materials needed for a Tesla coil can actually be found at a hardware store. For my primary coil, I use 3/8" copper refrigeration tubing as the conductor. Now a white conductor is really important because the skin effect makes thinner wire quite resistive at radio frequencies. I made some mounts out of acrylic to hold the primary windings in place, and then mounted it here on this coffee table. On the primary side, I needed a tank capacitor rated for the grueling high voltage, high current operating conditions of a multi-kilowatt Tesla coil. But off the shelf, these are very expensive. Now some people make their own capacitors out of things like beer bottles and foil, but these tend to be quite lossy. I ended up meeting in the middle by building a bank of smaller pulse capacitors, which gives great performance at a much lower cost. For the secondary side, I needed a coil with over 1,000 turns. Now I started winding one by hand, but without access to a lathe, this task turned out to be quite painstaking. So I ended up just giving in and buying a fully wound coil on eBay for $60. 4.5 inches wide, 22 inches tall, and 1,200 turns. Now I stuck a small top load from a much less awesome Tesla coil on top to increase the capacitance on the secondary side. The final piece of hardware to add was something to switch the primary tank circuit at well over 100 times per second, while also allowing the capacitor bank to charge up before firing. Now, I don't even want to know the cost of transistors actually rated for something like this. So I ended up following the path of many other Tesla coilers of the past, and built an asynchronous rotary spark gap. I started with the absolute cheapest angle grinder I could find, which turned out to be a $14 unit from Harbor Freight. Now for the spinning disc I used Bakelite, because it's both a great electrical insulator, and it's also tolerant of high temperatures. So I cut it into something close to a circle, and yeah, I was never quite the arts and crafts kind of guy. So I stuck it on a bench grinder and then ran it against a file. And after a few lungfuls of formaldehyde later, I had a nice circular disc. I mounted brass acorn nuts as the flying electrodes, and then used brass bolts for the stationary electrodes. Now when the angle grinder spins the electrodes into place, the 10,000 volts jumps the gap and allows the primary circuit to oscillate. Now when the gap fires, it is incredibly loud, nearly deafening. And it's funny because there's probably even a little bit of laser emission coming off that gap, considering the ambient nitrogen that's getting zapped by the high voltage. And here is the completed driver. It definitely looks terrifying. And I went ahead and added some warning stickers there, just to keep people safe. Then also one thing I want to point out is I added 10 of these microwave oven capacitors here to act as a capacitive ballast. And then over here I have my spark gap mounted, and there's my capacitor bank. So yeah, I guess we're ready to try this thing out. Now first I want to test this Tesla coil without the plasma globe on top. That way I can compare it to the original plasma globe driver. Because the plasma globe driver doesn't even make any visible corona when it's ran in open air. So let's see if this Tesla coil is any different. Alright, here we go. Man, why do I even do this kind of stuff? It's hard to convey just how loud that spark gap actually is. So the new plasma globe driver clearly works, and it actually produces sparks in midair unlike the old driver. But I guess that was expected considering this new driver draws 350 times as much power as the old one. So it's time to actually test this thing out with a plasma globe attached. And I added this nail here as a breakout point. That way I can feed the output of the coil directly into the globe. But in hindsight, I should have used iron for this because iron has a very high magnetic permeability. So its equivalent resistance to the skin effect is going to cause very high losses. But truth be told, I'm actually shooting this part after the fact and I've already blown up all my plasma globes. So... there. Now it's art. Alright, here we go. Let's hope it doesn't explode on the very first run. Check out those amazing patterns. But still though, it's not shooting arcs out of the glass. But I think I can fix this. Just like I did earlier, I'm going to stick some aluminum foil on top. That way it capacitively couples to the top of the coil. And it's funny because at these frequencies, whatever capacitance that this arrangement has is going to have an incredibly low impedance. So the arc should just shoot straight through the globe. Ah yes, there's that wonderful arc that I was after. It shoots 2 feet out of the top of the globe, which I think is pretty impressive. But maybe could we do even better if we add more foil to the thing? I used aluminum tape this time instead of foil, because it sticks to the sides better. And now this time I actually have 5 pieces as opposed to 1. So let's see how this thing performs. You know, it's funny. You'd think after all the time I just spent building this new driver, I would have remembered to actually attach the plasma globe to the thing. But as they say, science can't move forward without breaking some omelets or whatever. I stuck another globe on the driver, and this time used some zip ties to keep it held down. Now for my next experiment, I want to see if I could use this thing to remotely power up another plasma globe. Try doing that with an off-the-shelf plasma globe. Let's give that a try with some fluorescent tube lights, aka the much less awesome plasma globe equivalent. Now I know what you want to ask. Is the new plasma globe a fire hazard? Well, let's test it with some very special balloons. Amazingly, for all the experiments you just saw, I was only running the power supply at half the power I built it for. But even so, the voltage it generates is so high that it arcs back to itself. Now on the left, it hit the grounded strike rail, but that's fine because that's what it's meant for. But on the right, the strike came back and hit the secondary coil, and it's only going to take a few more of those to completely destroy it. So in future videos, I'll be sure to add a much bigger top load, and then see if I can pull off doubling the input power. Now I feel like I'm going to get some complaints about the title of this video, because my plasma globe was just overvolted, now overclocked, right? Well, it technically was overclocked. And no, it can't run Crysis, but the original driver had a frequency of 23 kHz, and the new one actually has a frequency of 265 kHz, so it's actually been overclocked by a factor of more than 10. But yeah, it was totally clickbait. Alright, so that's enough insanity for today, and I actually think this is going to be my longest video yet, so if you actually watched the entire thing, I'm pretty impressed. But first I'd love to give a big thank you to all my patrons on Patreon, because if it wasn't for all your generous support, I wouldn't be making videos for YouTube anymore, so a big thank you to you guys. In fact, I'm going to let you guys see this video first, before I make it public anywhere else. And yeah, you guys should also check out my Instagram page, because I post a lot of project updates there before you see them anywhere else, so there's a link in the description, be sure to check that out. And yeah, until the next time, stay safe and happy lazing.